So now in this video we're going to look at voltages again, just a basic circuit. So right now I got 1 volt to the power supply. The LEDs are blocking over 2 volts. And so that is just kind of bouncing back and forth because apparently it doesn't like to be at 1 volt for some reason. There we go, 2 volts, it's stabilized. You can see that the LEDs are not lit at all. Actually, they got a slight glow. And interestingly enough, the 1 kilo ohm one has a little more of a glow. Should have less current trickling through it. But that's all it is. It's just trickle current. Little current trickling through and a little bit of light. So we hit the button, and again, it's kind of interesting. The 1 kilo ohm protected LED is pretty bright. So actually, maybe this is just a freakish LED. I'm going to swap them really quick and put that one there and that one there. So yeah, actually, yeah, it's kind of weird. In person, that looks quite a bit dimmer. So that one's a naturally brighter one. So that was kind of interesting. But in any case, what we're going to do is, this current is actually that LED. You can see when I pop it out, it drops to nothing. There's hardly any current going through that one right there. And so I'm going to put another green LED in series right now. And we'll put the resistor back. And so there's 2 of them in series. Their voltages add up. And so we're going to have to increase the voltage. So for series LEDs, having higher voltage is not such a bad thing. But there you can see that the LEDs are all plenty bright right here, but we get 2 of them thanks to 1 resistor there, and we get 1 thanks to 1 resistor there. So more of the energy is going to heating up the resistor than providing light on this side, whereas more is providing light on that side. So now we're going to pop that out again, and you'll see the current actually held steady. So we may, actually I missed one, there we go. And that was probably too much current going through the LED. Let's see what, that may be one reason why that other LED was not so bright. But 20 milliamps of current, okay, we're still safe. So that was about 18 going there. So I got to be a little more careful when we have more LEDs. So I'm going to pluck that, put another LED in series, again being careful that it's actually in series, and now being careful that I actually get to the resistor of that one. So the 3 of them are in series, and they're not lighting up because we don't have enough voltage. So the voltage is adding up. But there you can see we're getting to about the same brightness as that one over there. When I pluck the resistor, you can see that actually most of the current was going through there. But we're proving a point here. We're going to add another LED in series right there. So you can see that we got 3 there, but if I go up 1 more row, we got, well, we'll have 4 once we raise the voltage enough. And so a 1 kilo ohm resistor can protect an LED pretty well up to about 12 volts. I think you can put the 1 kilo ohm resistor directly across the rail, but it's getting quite hot there. So in any case, we got 12 volts right now, and I want to inch this up a little closer. There we go, 13 volts. We have 20 milliamps of current, so we got about 10 on each side. And so if I remove either one or the other, that's the current of the 2, you can see it drops down to 10 milliamps of current right there, 10 milliamps. So 10 milliamps on both sides. Again, being careful because this is a low value resistor. So working with higher voltages, you need a higher value resistor to limit current, which doesn't sound too bad at first. But here you can see we're only lighting 1 LED on this side, whereas we're lighting 4 LEDs on that side. And this is really, it kind of looks like there's even the camera's having kind of a trouble seeing. They look like little fireballs, but they're pretty bright, even at 10 milliamps going through them. So it's going through them. And we're getting 4 on one side, so there's 4 times the light being produced with the same voltage, the same current going through them. So this circuit is using up as much power as this one here. They both have 13 volts across them. They both have 10 milliamps of current going through them. That's how you calculate power. But the power is being split up more on this side. It's being split up probably somewhat evenly between these 5 components. Whereas this one, since that LED is the same brightness as just one of those, the energy that these other 3 ones are in relationship to that resistor are going onto that resistor. So this resistor is getting a lot hotter. And so now I got the FLIR camera here, and it's showing up pretty good here. So there's the 100 ohm resistor, and there are the 4 LEDs that it is protecting, and there is the LED that the 1000 ohm resistor is protecting. And you can see the 1000 ohm resistor is really hot. And so I'm going to put my finger there in comparison, and there we go. So it looks like this shows everything in relationship to everything else. So we got more warm area total because my finger's there, and so it's making a lot more stuff blue. But it's pretty clear that resistor right there is a lot hotter than everything else. And so doing the math quick, we have, since we have 10 milliamps on each side, and maybe the LEDs are letting a little more current go through, maybe they're blocking a little less voltage because they're getting warmer, and because that was saying 20, now it says 21. But I did the math. We got 1 volt across the 100 ohm resistor. That makes sense. You would get 10 milliamps. And so 1 volt across it and 10 milliamps, you multiply them together and you have 10 milliwatts, 0.01 watts. Whereas the 1000 ohm resistor, we got 3 volts across the LED. That's no big surprise. And about 10 volts across the resistor. And the resistor is letting through 10 milliamps of current. So 10 volts times 10 milliamps of current is 0.1 watts, or 100 milliwatts. So this is rated for 250 milliwatts, which is a quarter watt, and we got it doing about 0.1. So you want to keep it close to about 0.125 watts, an eighth of a watt. And we are below that, so we're pretty good. So now, as we saw, we could see a lot with the power supply, but really the multimeter is where you get your good information, and you can get a lot more information, more accurate too. So in any case, red probe stays in this spot for everything but very high current. COM is always in that spot for this particular meter. This meter is auto ranging. All I have to do is go to voltage. Some of them, there's a range of voltages. You got to pick a number that is higher than what you can expect to measure. So in this case, it's 13 volts. And so it'd have to be something higher than 13 volts. But in any case, we can see what we're actually getting at the rail, which is actually going to be slightly less than we set with the power supply. So there's the alligator clips to the power supply there. They're clipped to jumpers. So there's a little extra resistance where those clip, and then hardly any resistance through the wire. But there's connection points there. The connection points have a little more resistance. And then connection points over to here. So this side may be slightly lower, even more, because there's a little more connection points. But it's doing pretty good right there. So the more metal on metal contact, the less resistance there'll be, and the better the voltage will travel. So in any case, let's look at the LED over here. So it's 13 volts, and as you can see on this side, we have 3 of those volts across one LED, whereas the resistor has about 10 volts across it, which makes sense. It was about 10 milliamps of current with a 1000 ohm resistor, so we expected about 10 volts across it. So now on this side, each one of the LEDs has about 3 volts across it. So I know it's hard to see what's going on, but I'm just going to slowly go down one row, and you'll see that we're getting 3 more volts each time. So I'm across 3 of the resistors at about 3 volts, about 9 volts right there. And we go to the top here, and you can see it's about 12 volts once I get a connection. It's really hard to see. So about 12 volts. and we got a 13 volt power supply. That leaves about 1 volt left across the resistor, 100 ohm resistor. And so you put 1 volt across a 100 ohm resistor, you get about 10 milliamps of current. So we got that there. Now we're lighting one LED on this side. We saw most of the voltages across the resistor. We're lighting 4 LEDs. So we're getting something useful. The heat from the resistor, we don't usually consider that useful unless we actually want to heat something up for some reason. So there are heaters, electric heaters, so you don't consider that wasted energy because you want that heat. Whereas in this case, we got the heat going into the air, and it's Minnesota, so actually it's kind of helping heat the house a little bit. But the resistor for most part is just wasted heat. Usually you want to get rid of that heat, and you may have to power a fan or something to do that. And so it's no big deal with a power supply like this. I'm getting power, through the outlet, and so this is just changing. It's taking about 120 ohms, 120 volts. That's alternating current, and it's making it go into one direction and then smoothing it out basically, and also lowering the voltage in this case to 13 volts. And so like a speck more coal is being burned or something to provide this. But if we were using a battery, so batteries have a bunch of cells, and so the higher the voltage, you just stack more cells onto them. And so for both of these, if it's a lead acid battery, let's just say, because they have about 2 volt cells approximately, and so we would need actually probably like 7 of those cells for 14 volts, but 6 of the cells is about 12 volts, so we'll work with that. So you got 6 cells there that are lighting these up on both sides. And so for the 4 LEDs, you're getting 4 times as much out of that energy being used as 1. So you're draining 6 cells, but in this case it's to light 4 LEDs. In that case it's to light 1. So it's a waste of energy for the most part. Whereas if we pluck that resistor and we go down to 4 volts, which would be 2 cells, we can take the resistor here and there you can see we got 10 milliamps of current. Let's get the multimeter out of the way. We got 10 milliamps of current with the 2 of them, and if I pluck that one, there you can see it's still about 10 milliamps of current. So if all we want to do is light 1 LED, much better to use 4 volts, which would be 2 lead acid cells and a 100 ohm resistor. Whereas if we want to light one with a 1 kilo ohm resistor, we had to go all the way up to 13 volts to get 10 milliamps. So that's a lot more cells. Those cells are pushing current through and draining. You have to put energy to recharge all of them. You're just wasting energy. So that was the point of this video, basically, the wasted energy. And you want to try to keep the voltage as low as you can. 5 volts is common though. You can see we got the 5 volt plugs there, and so that's generally what I design my circuits by. So I don't design the most efficient circuit. If I was, I would get the lowest voltage possible. Normally I do 5 volts now, and so now we got almost 20 milliamps of current just by bumping it up to 5 volts. So in this case, that's what I would mostly do. A single LED with 5 volts, getting close to 20 milliamps. These LEDs have a limit of about 20 milliamps. Don't go above that though. But that's the other thing. Make sure you got enough resistance that the LEDs don't get more than 20 milliamps of current. So in any case, this video went on quite long. I hope you still enjoyed it. And so like I said, I try to keep that at 5 volts. I'm going to turn the power off so the LEDs go off. I try not to leave it at a higher voltage because I'll forget. I'll wire something up for 5 volts, turn it on. The higher voltage might fry something. So, hope you enjoyed the video. Make sure to click one of these other ones. Click the subscribe button and the bell. I will see you in the next video.